As we study gases and the ways in which pressure, volume, temperature, and the number of moles are related, we will discover along the way relationships, mathematical relationships, that we will call gas laws that help us understand how the various variables relate to one another. And what I'm going to do here is just go through very quickly the gas law relationships that you will have occasion to use, and then we'll look at some examples following this slide. The first law, named Charles' law, requires that the pressure and the number of moles, N, P and N, be constant. Now what does that mean? It means that if you're going to be using Charles' law, pressure and the number of moles of gas must not change throughout the problem that you're working. If for some reason pressure or N change, then Charles' law is not the law to be using. The relationship is quite simple. Volume is proportional to temperature. This means, since it's a direct proportionality, that if temperature goes up, volume goes up. And conversely, if volume goes up, temperature should go up. Mathematically, we can say that the ratio of the volume to the temperature is always a constant. And what this lets us do is, for any given problem, if we calculate the volume to temperature ratio using some given information, say at the start of some problem, then that ratio is going to be a constant, and we can use that constant to determine other ratios. Say if we only had the volume but needed the temperature for the second half of a problem, then if we knew the constant and we knew the the final volume, then we could solve for the final temperature. Moving on to another law, Boyle's law. Boyle's law requires that temperature and the number of moles be constant. Again, if these two variables are not held fixed throughout the problem, you don't want to be using Boyle's law. The relationship is an inverse relationship here, where pressure is inversely related to volume. This means that an increase in volume corresponds to a decrease in pressure, and vice versa. Mathematically, the equation that we get simplifies a little bit less complicated than Charles' law. It says that the product of the pressure and the volume should always be a constant. And so if we have initial conditions that permit us to calculate that constant, Pi times Vi, then we can use that constant throughout the problem as we calculate other combinations of pressure and volume, say Pf and Vf. Well, how many times can we turn this combination of variables around? Well, there is another. There's Avogadro's law, and Avogadro's law requires that temperature and pressure be constant. The mathematical relationship is a direct proportionality, again, where the number of moles is directly proportional to the volume. And so if the number of moles of gas increases, then the volume should increase. Now, a simple example of how Avogadro's law works: if you're blowing up a balloon, what you're doing with your lung power is you're forcing additional gas molecules into the balloon. And as that number of gas molecules increases, N, of course, increases, and all other factors being held constant, or roughly so, the balloon has no choice but to get bigger. And so as the number of moles of gas increase, you're pushing them into the balloon grows in size. Mathematically, we can work problems using this relationship, as the volume to number of moles ratio should be held constant throughout the problem. And again, we calculate that constant at one point in the problem, and then we can use that constant in later parts of the problem. One of the last ways that we can rearrange these gas law relationships has to do with the combined gas law. Now, the combined gas law differs from the previous three in that it requires that only the number of moles of gas, N, be held constant. And so this is the only thing you need to assure yourself of before you use this law. And it says that the product now of pressure times volume is proportional to the temperature. Okay, in problems where you can assume that the number of moles, N, is constant, you can use the combined gas law to discover how pressure, volume, and temperature are interconnected. And the arithmetic looks a little bit like this. We have the product of pressure times volume in the numerator of the fraction and temperature in the denominator of the fraction. And this combination, this ratio of PV to T, is always a constant throughout the problem. Typically, the way problems like this work out, with some initial information, a pressure, a volume, and a temperature, you're able to calculate the constant K. And then the problem goes on to ask something about some other variable, and you will use that value of K as you solve the second half of the problem. Let's take a look at gas law behavior by first singling out Boyle's law and looking at an application of how one would use the idea that pressure times volume is a constant. Okay? And again, this is going to assume that N and that T are going to be constant and unchanging throughout the problem, and that the only variables, the only things that can change, are P and V. Boyle's law tells me, though, that P and V are not independent of one another, but that their product must always give us some constant value. The problem we're going to look at has to do with the scuba diver, as you can imagine. More importantly, it has to do with her lungs. We're going to look at how her lungs, being somewhat related to the balloon that we talked about on our first slide, how the lungs are going to respond throughout the dive. Now, before we begin the dive, let's just imagine the scuba diver up here at the top, that they're swimming out in the sea someplace, and that the weight of the atmosphere above them is such that atmospheric pressure is 1 atmosphere, not an unreasonable atmospheric pressure for sea level. Okay, so we've got the diver up there. The atmospheric pressure is pushing down on them. How does that change for the diver at depth? Specifically, if they're 33 feet underwater. Now, this isn't an arbitrary number, as you'll soon see. At 33 feet, we know that the atmospheric pressure is still pushing down on them. Okay, atmosphere is still 33 feet above them, but the weight of the atmosphere is still there and still continues to push down on them. But that's not the end of the story, because at 33 feet, the scuba diver has an incredible weight of water pushing down on her as well. And this contributes to something that we could refer to as the water pressure. All right, so now we have both the atmosphere and the water pushing down on the scuba diver, pushing down on her lungs. And if we look at how these two combine, the pressure of the atmosphere is 1. The pressure of the water, now this is specific to 33 feet. At 33 feet, the water pressure is an additional 1 atmosphere. You combine that now with the weight of the atmosphere. We've got atmospheric pressure plus the water pressure in blue, and the scuba diver, well, she experiences a total combined pressure of 2 atmospheres. You see, the weight of the water at 33 feet contributes this additional atmosphere's worth of pressure. Just for the record, if you were to go down to from 33 feet to 66 feet, for every 33 feet additional you go down, you contribute 1 more atmosphere of water pressure. And so the total pressure, if we were to do this problem at, say, 66 feet instead, would be the 1 atmosphere of the atmosphere, a little redundant, plus 1 atmosphere's pressure for the first 33 feet, plus another atmosphere's pressure for the second 33 feet, or a total of 3 atmospheres if we were doing this problem at 66 feet. But we're not. We're going to keep it at 33 feet, and the scuba diver then experiences this combined pressure of 2 atmospheres. All right. Now, let's employ Boyle's law to see what other information we can derive from the problem. As part of the given information, we'd need to know that the volume of our scuba diver's lungs was 5 liters, approximately correct for a typical adult. Okay. The pressure, we've already noted, is 2 atmospheres. Well, we've got pressure and volume, and if we assume Boyle's law works, that is, if we assume that N and T are held constant, then we can calculate what PV is equal to. An important constant. Pressure times volume is 5 times 2, and that's equal to 10. And the units, well, the units of pressure and volume just carry over. Volume is liters, pressure is atmospheres, and so the constant that we calculate is 10 liter atmospheres. Well, good. If Boyle's law is going to work throughout this problem, then we know that whenever we've got pressure and volume, the two multiplied together, they must give us the same 10. Now, let's imagine what happens if the diver surfaces. And let's also imagine a very dangerous thing. It's not recommended that divers ever do this, but let's imagine what would happen if the diver held her breath. Now, what is this doing? It's insisting that no air escape her lungs. That's another way of saying that the N, the number of moles of gas in the balloons, that is the lungs, isn't going to change. And so we're going to ask that she hold her breath, and that along the way, this is another way of saying that N is constant, and we're going to assume that the water temperature is approximately the same from top to bottom too. And so, assuming that N and T are constant, which was a premise to being able to use Boyle's law, we then need to think about what's happening or what has happened to the diver as that diver now has reached the surface. Now, one thing is for certain, and that is that P times V is still a constant, and we still have the pressure of the atmosphere pushing down on the diver at this point. Okay, so mathematically, we have P times V is equal to 10 liter atmospheres. That hasn't changed. We derived that for the diver at depth. Now, if we solve for V, then V is going to be equal to 10 liter atmospheres divided by P. Okay? Just a little bit of algebra there. Do we know anything more? Well, we do know that it's atmospheric pressure now for the diver at the surface. They no longer have the weight of the water pushing down on them. And so we can take 1 atmosphere and plug it into this equation. So we now have volume is equal to 10 liter atmospheres divided by 1. The arithmetic couldn't be simpler. And we can calculate then that the volume of the lungs is now 10 liters. Now wait a minute. We just said that the volume of the lung was 5 liters. Well, that was true. The normal adult's lung volume is about 5 liters. But by holding her breath, the scuba diver has put herself in a very dangerous situation. You see, by holding her breath, the number of moles of gas never changed. Air was not allowed to leave the lungs. But there was so much air in her lungs that on the way up, as the pressure around her decreased, the lungs were forced to expand. And they expanded from 5 liters to 10 liters. They doubled their size. If the diver were to actually do this experiment, it's quite likely that they would suffer serious injury, since the average adult's lungs is not 10 liters large. In fact, having had some scuba diving lessons, one of the things they always tell you to do is that as you're rising up, as you're surfacing, you should always be blowing bubbles. And in a way, what they're telling you to do is to release that excess pressure, that excess gas that's trapped in your lungs. It was fine when you were submerged at 33 feet, but at atmosphere, there's way too much gas in your lungs for your lungs to be able to surround and encapsulate all that volume. So, long story short, when you're a scuba diver, you're always blowing air out as you surface to let the excess air out, such that the volume of your lungs is not forced to increase to this ridiculous 10 liters figure. The pressure halves. We go from 2 atmospheres to 1 atmosphere, and the volume doubles. Again, an inverse relationship as Boyle's law is supposed to be. Just as a last note, holding your breath while scuba diving is discouraged and is in fact very dangerous, as the volume of the lung would increase to beyond the limit of the lung, and you would probably suffer some serious injury. Well, let's take a look at one more gas law. This is Avogadro's law, and Avogadro's law is only going to be valid when pressure and temperature are constant. If you can assume that pressure and temperature aren't going to change throughout the problem, then Avogadro's law is the law for you. And Avogadro's law says that the ratio of volume to the number of moles of gas, N, is always going to be a constant. If you double the volume, then you must also double the moles of gas under these conditions of constant pressure and constant temperature. Now, an interesting thing that comes up that we've assumed all along through our discussions of gases and gas laws is that the identity of the gas doesn't matter. This is really very interesting. You mean that it doesn't matter that I might be using nitrogen gas on one hand or perhaps neon gas on the other? Why, don't you think it should matter? One's a diatomic, the other, neon, is a monatomic gas. And yet, to a first approximation, the identity of the gas doesn't matter. What does matter is that the gas consists of small particles, and no one can argue that a nitrogen molecule and a neon atom are small particles, are flying around madly within a space, having collisions with the walls of whatever balloon we might be pushing them into. And so the identity of the gas, at this point anyway, doesn't matter. Okay, let's imagine that we've got two different gases and we've stuffed them into a balloon. The first balloon contains 1 mole of helium and the second balloon contains 1 mole of nitrogen. Helium is a monatomic gas. Nitrogen is a diatomic gas. It consists of pairings of nitrogen atoms, a nitrogen bonded to another nitrogen, a nitrogen molecule, if you like. Okay, and in each case we've got 1 mole. What does that mean? It means that In either balloon, I have 6.022 times 10 to the 23rd particles. And that's as much detail as we need to think about. We're also going to specify some conditions. After all, Avogadro's law only works when you have constant pressure and constant temperature. And so the temperature we're going to assume, in this illustration anyway, is that we have 0 Celsius, 273.15 kelvins. And the pressure is equal to a perfect 1.00 atmospheres. Now, set up in this way, with 1 mole of gas in either balloon, the temperature just so, the pressure 1 atmosphere, then the volume of both balloons will be 22.414 liters, independent of the identity of the gas. Now, these conditions of temperature and pressure are so important that they have earned themselves a special name. They're called standard temperature and pressure. Standard temperature is 0 degrees Celsius, standard pressure is 1 atmosphere, and we abbreviate that as simply STP. STP means standard temperature and pressure. Now, if you're working a problem and the letters or an explanation in the problem says, under the conditions of STP, they're giving you some really important information, right? Because they're telling you the temperature is 0 Celsius and they're telling you the pressure is 1 atmosphere. And so when you see STP in a problem, be sure you understand that that is additional information. Even though the numbers may not be written, it's assumed that you understand what STP means. Now let's back off for just a moment and think about these balloons again. In either case, we've got a balloon with 1 mole of particles in it, either helium or nitrogen. And under the conditions of STP, this 1 mole of particles occupies 22.414 liters of space. 22.414 liters is known as the molar volume of an ideal gas at STP. In other words, it's a conversion factor of sorts. If you can be sure that the conditions of STP apply to your problem, then you can be assured that 1 mole of whatever gas happens to be the concern in that problem is the same as 22.414 liters. These are interchangeable. 22.414 liters is equal to 1 mole. Well, what happens if the balloon is, say, 44.828 liters? Well, 44.828 liters is twice the space. Therefore, at STP, I don't have 1 mole, I have 2 moles. Twice the amount of volume must mean twice the number of moles. Let's continue our study of gas law relationships by looking at the combined gas law. A bit more powerful, it includes pressure, volume, and temperature as the variables, but it assumes that the number of moles of gas, N, isn't going to change anywhere throughout the problem. Okay, let's have a look at the problem. What you're seeing is a stratospheric weather balloon. It's the sort of balloon that's used to fly scientific instrumentation way, way up into the atmosphere, many miles. This balloon that you're looking at is actually in the process of being launched, and one thing may strike you is that the balloon doesn't really look like it's filled up properly. The truth is that there is a certain amount of helium gas that's been placed into the balloon, but the balloon, the bag that you see, and that long stringer that heads off toward the ground, that stringer is actually uninflated balloon. That balloon, if it were inflated, would be huge and likely would fill the entire picture. But in this case, at ground level, as the balloon is being launched, it's only been partially filled. Now what's going to happen? Well, as the balloon rises up into the sky, and you can see it here along with the instrumentation package below, it will eventually, when it reaches high altitude, fill completely. You see, the atmospheric pressure is so much less at high altitudes that the gas within the balloon can expand to fill the balloon completely and entirely, leaving it round as a basketball. And so we go from what appears to be an uninflated balloon or underinflated balloon to something that is very, very completely filled once it reaches altitude. Now, of course, the designer and the scientist involved in this experiment wouldn't want to put too much gas in to begin with. They need to anticipate this expansion, or if they do it incorrectly, the balloon, if underfilled, may not rise into the sky, but if overfilled, may burst before it actually reaches its working altitude. Okay, well, where can we go with this? We need some information. I guess we need a question first. What is the maximum volume that can be used? What is the maximum volume of gas, the initial fill, so that the balloon won't break or burst at high altitude? Okay, so we've got some initial launch information here. First of all, that the atmospheric pressure that day, just to keep things easy and simple, is 1.00 atmosphere. So this is the pressure of the atmosphere that's squeezing the gas in the balloon into a smaller space. The temperature is 25 degrees Celsius. Now recall from our first slide, the temperatures also must be measured in Kelvin units, not in Celsius units, and so I've put in parentheses there 25 Celsius converted into 298.15 kelvins, and it's the Kelvin temperature that we need to use in this example. We don't know how much gas needs to be put into this balloon to begin with, and so the initial volume of gas is unknown and will be our variable. Now, in the troposphere, 10 miles up into the atmosphere, where the air is very thin, the atmospheric pressure is a tenth of what it is for us on the surface. And so the atmospheric pressure has decreased dramatically. And as a result of that, the gas inside the balloon will be able to expand because there's less atmosphere squeezing down on it. The temperature has also dropped. Minus 57 degrees Celsius translates into 216.15 kelvins. And it's that Kelvin temperature that we're going to need to use. The volume of the balloon, well, the balloon is going to be maxed out at altitude. At 10 miles up, the balloon is going to be completely filled, not underfilled, not overfilled, because that would mean breaking, but filled just perfectly. And the volume of the balloon at altitude is known to be 3,200 liters. That's the maximum size the balloon can occupy. So, we've got a collection of information. There's some really nice symmetry here. On launch, we have P, T, and V, where V is our variable, and at altitude, in the troposphere, we have P, T, and V, and we've got numbers for all of those. Can't resist, want to use the combined gas law, and that is that PV divided by T is a constant, and we have, at altitude in the troposphere, every variable filled. We can substitute for pressure 0.1 atmospheres, for volume 3,200 liters, and for temperature, using the Kelvin temperature 216.15 kelvins. And the PV divided by T constant that we get is 1.4804 liter atmospheres per Kelvin. And that would be the PV divided by T constant K, not to be confused with the Kelvin temperature. Now, assuming that N doesn't change anywhere, assuming that no helium gas leaks out of the balloon as it rises up into the sky, then we're going to be able to use this PV over T constant way back at the launch. It should be the very same constant that we calculated in the troposphere. So, PV over T is equal to 1.4804 liter atmospheres per Kelvin. We can rearrange this and we can solve for V. V, if I multiply both sides by 1 over P, the P becomes the denominator, and if I multiply both sides by T, then T winds up in the numerator, and I've got volume is equal to temperature times my combined gas law constant divided by P. These are exactly the variables that I have information for at launch, the temperature and the pressure, and I can substitute 298.15 for T and 1 atmosphere for pressure. These are initial values, and I can solve for the volume, and the volume will be 441 liters. Let's try to wrap this all up and think about what it means. The scientist who fills the balloon needs to be sure that they put no more than 441 liters of helium into that balloon at the beginning before launch. To put in any more than 441 would mean that when that gas expands, it would expand to a space much larger than the volume of the balloon, which we found was 3,200 liters. So, 441 liters of helium will, under these circumstances, expand to fill the balloon at 3,200 liters when the balloon reaches an altitude of 10 miles in the troposphere. This represents 13.8% of the original volume if you were to do that comparison. Okay, so I've suggested how one might actually use molar volume as a way of converting between moles and liters. So here's a problem from your book that would help illustrate this. When 35.6 liters of ammonia and 40.5 liters of oxygen gas at, ta-da, STP burn, okay, STP, we know what that means, nitrogen monoxide and water are produced. After products return to STP, how many grams of nitrogen monoxide are present? Whoa, this looks like quite a problem. Let's see if we can't flesh it out a little bit. So, the balanced chemical equation from the book looks like this, and we see that we have 4 ammonias combining with 5 oxygens to form 4 nitrogen monoxides and 6 water molecules. Okay, so far so good. That looks like an equation we can manage. We know that this is a problem that's been stated under conditions of STP. So let's put the information from the problem where it belongs in the balanced chemical reaction. STP, remember, is 1 atmosphere's pressure, temperature 0 degrees Celsius, and we have 35.6 liters of ammonia and 40.5 liters of oxygen gas. Along the way, back in Chapter 4, I believe I suggested, or maybe even more strongly suggested, that whenever you are given a problem where you're given amounts of both reactants, bells and whistles ought to be going off, because this is likely to be a limiting and an excess problem, and this is indeed the case here. We have an amount of gas, okay, it's liters, but we can deal with that, for NH3. We have an amount of gas for the other reactant, for the O2, and that's 40.5 liters. We know something about both of the reactants. It's quite likely that it's going to be a limiting and excess kind of problem. What we're going to do is we're going to convert 35.6 liters into moles and then use the reaction ratio to determine how many moles of nitrogen monoxide should be produced from that amount of NH3. We're going to work a parallel problem, and we're going to work it in exactly the same way, except we're going to begin this time with the oxygen gas. The 40.5 liters of oxygen, we'll convert that to moles, and then use the reaction ratio to find out how many moles of nitrogen monoxide are going to be produced. Limiting and excess problems like this, we always wind up working 2 different problems, and then when we arrive at the destination, and the destination is nitrogen monoxide in this case, we look over the 2 possibilities and we always choose, do you remember? You always choose the one that predicts the smallest amount of product, and that's the amount of product that will really be produced in the reaction. It will be associated with the limiting reactant. Okay, so let's start with 35.6 liters down there in the lower left-hand corner. We're going to work the problem in red first, and we need to convert 35.6 liters into moles. Well, we have the molar volume of a gas from the previous slide, and we are also assured that these are conditions of STP. So we know that the standard temperature and pressure requirements are being satisfied here. And so we can multiply by the conversion factor that relates the moles of nitrogen, the moles of ammonia to the liters of ammonia. And that's just the molar volume of the gas, 22.414 liters to 1 mole. This will, in effect, accomplish the conversion to moles. And if you stop at this point, you will get 1.59 moles as the number of moles for NH3 in this part of the problem. But we don't want to stop there. I've filled in the number, 1.59, there in the mole space, but let's keep going. We also know that the mole ratio that connects NH3 to nitrogen monoxide is a 4:4, or better yet, a 1:1 ratio. And so we can carry that forward. It would be 1.59 moles of nitrogen monoxide. We predict that 35.6 liters of NH3 in red should produce 1.59 moles of nitrogen monoxide. Perfect. Half the problem finished. Now, we're going to work the purple part of the problem just to see how its prediction comes out, and then we'll compare this to 1.59. Working the purple part of the problem, beginning with oxygen gas, we have 40.5 liters of oxygen gas. Good. We know that STP conditions are satisfied, and so we're going to be able to use the same conversion factor, the molar volume of a gas, 22.414 liters per mole, except now it's being applied to oxygen gas, and again, the identity of the gas doesn't matter. And then what do we get? Well, if you stop there and hit equals on your calculator, you will get 1.81 moles of oxygen gas, and I filled that into the blank. The next step requires that we know the reaction ratio that connects oxygen to nitrogen monoxide, and this, unfortunately, is not a 4:4. It's actually a 4:5, taking the coefficients from the balanced chemical reaction. And if we hit equals on the calculator after multiplying by 4 and dividing by 5, we find that the number of moles of nitrogen monoxide predicted using oxygen as a starting point will be 1.44. Awesome. We're at a good position now. We've got both of these problems solved. All we need to do is to look at the amounts of nitrogen monoxide, 1.44 predicted from oxygen, 1.59 predicted from NH3, and then choose the smaller one, because that's the one that's actually going to be produced. So, smaller ones clearly, 1.44 moles of nitrogen monoxide. This would be the answer if it weren't for the fact that the question was not how many moles of nitrogen monoxide are present, but how many grams. And so, in italics above NO in the balanced chemical equation, I've given you 30.01, which is the molar mass of nitrogen monoxide. And you can use that now to convert 1.44 moles of nitrogen monoxide into grams of nitrogen monoxide. The limiting reactant is O2. The excess reactant would be whatever else you had, the NH3. And let's do the arithmetic. Here I'm converting 1.44 moles of NO into grams of NO using the molar mass, and the answer to the problem would be 43.4 grams of nitrogen monoxide, produced by the limiting reactant. The combined gas law, PV divided by T, suggests that there might be ways of combining all of the variables, the four variables, the pressure, the volume, the temperature, and the number of moles, into one tidy, neat little equation. And the truth is, that's exactly what we're going to be doing with what's known as the ideal gas law. Frankly, this is the only gas law that I remember. All of the gas law problems I use only the ideal gas law with. The ideal gas law tells us that the ratio of PV to NT is always going to be a constant. We've incorporated into this ideal gas law now all of the conceivable variables: pressure, volume, number of moles, and temperature. And it's the ratio of PV to NT that's going to be a constant throughout the entire problem. However, because we've used all of the variables, we've accounted for all four variables, this constant is more than just an arbitrary constant that applies to one particular problem. It's actually a universal constant called the ideal gas law constant, R, or the universal gas law constant. So the ratio of PV to NT is always going to be equal to, assuming ideal gas law behavior, the same value of R, regardless of the problem that you're working on. The value of R depends upon the units that you're using. In some cases, the gas law constant is 8.31447 with units of joules per mole Kelvin. This is a value I do expect you to memorize. In other applications, the value of R, it's a different numerical value. It's still a constant, but the reason it's different numerically is because it has different units. 0.0820578 is the value of the gas law constant if you're working a problem that involves liters, atmospheres, moles, and Kelvin. And so which gas law constant you choose is going to depend upon what the units happen to be in the problem that you're working. The ideal gas law is often remembered as PV equals nRT. Just a little bit of rearrangement. We've moved the NT over to the same side as the gas law constant R. PV equals nRT is how I remember it, and I believe it's how many chemists and scientists remember it as well. But it's just a different rearrangement. Let's talk about what these variables are, just as a quick review. P is pressure, and frequently will be in atmospheres. Volume, again, a measure of the amount of space and measured in liters. And the number of moles, we would have used Avogadro's number, or 6.022 times 10 to the 23rd, to get that number of moles. R is the gas law constant, and in problems that we're going to be working at least first, the gas law constant that we'll be using will have units of liter atmospheres per mole Kelvin. And temperature, don't forget, the temperature always has to be in Kelvin units. Don't forget about that temperature conversion that you may have to do if you're given Celsius units to begin with. Some rearrangements that are useful. If you want to solve for, or if you're asked to determine the number of moles of gas, we solve for N, and N is equal to PV over RT. Another rearrangement that's useful is that if you need to know the volume is nRT over P. And then one last rearrangement of all these variables. If the pressure is what you need, then it's going to be equal to nRT over V. I don't remember these. I don't memorize them. I just remember PV equals nRT, and then I do the necessary algebra to get the equation in whatever form happens to work for me for that specific problem.